Okay, so, oops, sine x over cosine x times sine x over cosine x plus cosine squared x, and we want to show that that's equal to sine squared x plus cosine squared x. Is that what you're... No. Is that, like, do you want to rewrite, or do you want to tell me? Oh. Okay. Okay, so these are, so let's see. So sine x over cosine x times sine x times cosine x times cosine squared x, like that, equals sine squared x plus cosine squared x. Okay. So, the first thing that I would do in this problem here is notice, so if you start with the left-hand side, right, sine x over cosine x times sine x times cosine x times cosine squared x. So the first thing I would notice is that one of the cosine x's and that cosine x would cancel each other out. Does that make sense? Are you sure that this isn't a plus sign here? Okay, no. I just want to make sure, because I was like, wait, I can't get what. Okay, so yeah, that should be a plus. Okay, so plus cosine squared x. So then on that first part, you're left with sine x times sine x. So that would be sine squared x and then plus cosine squared x. So does that help? I'm assuming since you said, oh, okay, it probably does, but I just want to make sure it does. Okay, and then Brendan, I think, had a question or gave me one. Okay, so Brendan, you're talking about 1 minus cotangent x, that quantity squared, and what did it ask you to do? Okay, but it had to tell you, like, it's equal to, to give you something it was equal to? That you're, okay, equals to, whoops, equal to cosecant squared x minus 2 cotangent x. Okay, so I would start with the left-hand side, right? So on the left-hand side, you have 1 minus cotangent x quantity squared. And so the thing to remember is what that means. So what that means is 1 minus cotangent x times 1 minus cotangent x. Right? And so all I did here was some algebra, right? And are you okay with that? Okay. So now if you FOIL this, right, I have 1 times 1, so that's going to give me 1. I have 1 times minus cotangent, so that's going to give me minus cotangent x. I have minus cotangent times 1, so that's going to give me minus cotangent x. And then I have cotangent, minus cotangent times minus cotangent, which is going to give me plus cotangent squared x. Are you okay with that? Okay. And so then again, that's just still some algebra steps. So if I put the like terms together, right, I have 1, I have 2 of these minus cotangent x's, so minus 2 cotangent x plus cotangent squared x. So again, that's just some algebra. And so if you look where we're trying to get to, right, my final answer that I'm trying to get to has a minus 2 cotangent x, and so now I have a minus 2 cotangent x, so that's good. So hopefully the other pieces together can make it a cosecant squared x. And so if we kind of regroup them a little bit and just said this is 1 plus cotangent squared x minus 2 cotangent x. So technically rewriting it is still just some algebra work. So remember 1 plus cotangent squared x, that is actually just cosecant squared x. So this is equal to cosecant squared x minus 2 cotangent x, and I used here the Pythagorean identity. Does that make sense? No problem. Any other questions? No? Okay. So then we're gonna finish today doing the like using the identities from the sheet, what we were doing last class. If you remember, I said these came from sections 5.2 to 5.4 continued, right? We started this last class. And so there were a couple different types of identity problems that we didn't do any examples of. And so those are the ones that I want to do some examples of today. So for example, find the exact value of the sine of cosine inverse of 12 over 13 plus tangent inverse of 4/3. So I basically have I have the sine of two things added together, right? So we were talking about last class how on our sheet we have a sine, there is a problem that says the sine of alpha plus beta. So we can think of this first part, the cosine inverse of 12 over 13, as the alpha, and we can think of this second part, the tangent of 4 over 3, as the beta. So basically, what I really have going on here is sine of alpha plus beta. And if you go to that sheet that I said how I put up on Canvas for you guys, the trigonometric identity sheet, right? This one that has all of these identities on it. Under sum and difference, there is one that says the sine of alpha plus beta. And if you look that up, it says that the sine of alpha plus beta is the sine of alpha cosine of beta plus cosine of alpha sine of beta, right? And so I just have to figure out what the sine of alpha is, what the cosine of beta is, what the cosine of alpha is, what the sine of beta is, right? I was given some information about alpha and beta. So from here, we're going to look at each one of these cases. So we're saying that alpha is equal to the inverse cosine of 12 over 13. So if you remember back to when we did the inverse trig functions, we could rewrite this. If alpha is equal to the inverse cosine of 12 over 13, what that is saying is that the cosine of alpha is actually equal to 12 over 13. And what I can do from there is I can actually draw a triangle and say, oh, here's alpha. And so the cosine is adjacent over the hypotenuse, 13. And then I can use the Pythagorean theorem to help me find the missing side. So a squared plus b squared equals c squared. So 12 squared plus b squared equals 13 squared. So 144 plus b squared equals 169. Subtract the 144 over, b squared is going to be 25. So b is going to be plus or minus 5. They're not giving me any kind of quadrants here or anything. We're just making the triangle, so we're going to take the positive part. So that side is 5. So the nice thing now is that I can use that to figure out, I can use this triangle that I just made here to figure out everything that deals with an alpha. So I'm looking for the sine of alpha and the cosine of alpha. So if I use that triangle, the sine of alpha, remember sine is opposite over hypotenuse, so the opposite is 5 and the hypotenuse is 13. So the sine of alpha is going to be 5 over 13. We don't know the cosine of beta yet, so we'll take care of the beta stuff in a couple minutes. The cosine of alpha, so the cosine of alpha is adjacent 12 over hypotenuse 13. So it's going to be 12 over 13. And again, I don't know the sine of beta yet. So questions on anything I've done so far? We're not done with the problem. We still have to do all the stuff that deals with beta. But I've taken care of all the stuff that deals with alpha. No? No other questions yet? How did I know the 5 is positive? Yeah, so that's a good question. So in this problem, like there's nothing that guarantees that the 5 is positive. However, in these types of problems, we're not trying to put the alpha into a quadrant. Since they just gave us like one little piece of information, and all the stuff is positive, we're just thinking of it as a triangle. And so since I'm dealing with it just as a random triangle, I want to think of it as like lengths. And so if I'm thinking of it as lengths, of stuff, then we're going to take positive because the measurement, like if we're talking about we're measuring something, measurements are going to be positive. You have to worry about the sign if they were like telling you information about the quadrant. So like if they still said, oh, the cosine inverse is 12 over 13, 13, and that angle is in quadrant 3. Then we got to worry about, well, it wouldn't be in quadrant 3, but it's in quadrant 4. Then we got to worry about whether we're talking about positive or negative. But here we're not dealing with like an angle that's in a quadrant. We're just kind of thinking of it more as just a plain old triangle kind of just sitting there in space. Does that answer your question? No problem. Other questions? Okay, so then let's do the same thing with beta. So we know that beta is equal to the tangent inverse of 4/3, right? Which means if I rewrite that, we're saying that the tangent of beta is equal to 4 over 3. So again, I'm making a triangle. So tangent is opposite. Oops, not alpha. This is beta. Opposite over the adjacent. And again, I can use Pythagorean Theorem. So 3 squared plus 4 squared is going to be c squared. So 9 plus 16 equals c squared. So 25 equals, c squared. So again, c we're going to take to be the positive. It's the hypotenuse, so no matter where it would always be positive. And so now I can figure out the cosine of beta. So the cosine of beta is going to be 3/5. And the sine of beta is going to be 4/5. Questions on how I got any of those things with beta? No. Okay, so now I just have to multiply these things, right? So if you multiply the first part, you end up with 15 on the top and 65 on the bottom. And if you multiply the second part, you end up with 48 on the top and 65 on the bottom. In the first part, you could have canceled the 5s, but I'm going to have to remake it to be 65 to make a common denominator to put the two fractions together. So that's why I didn't cancel anything at the beginning. And then 15 and 48 is actually 63. So I have 63 over 65, and I can't reduce that anymore. So the final answer here is 63 over 65. Does that make sense? Questions? No? Okay, so that's one of the problems. One of the types of problems we didn't see the other day. Kind of similar to it, there's another type of problem that's it's going to use the same type of thing, except here in this problem we had actual numbers here for when we had an inverse function. So we had, we knew this was 12 over 13, we knew this was 4 over 3. In the next problem, we don't actually have actual numbers. So rewrite the sine of 2 tangent inverse v over 3 as an algebraic expression in v. Okay, so basically, when they say rewrite as an algebraic expression, they want your answer is going to have v's in it. So it's going to be some combination of stuff with v's in it. This is going to be pretty similar to what we just did, right? So if you remember, what we just did was we let the inverse trig part, we had two different inverse trig parts. So we let one of them be alpha and one of them be beta. We're going to do a similar thing here. So we're going to say, let's let this inverse tangent part here be alpha. All right? So that's where we're going to kind of start. We're going to let alpha be equal to the tangent inverse of v over 3. So that's pretty similar to what we did before, right? And then what we did on the last problem is we rewrote it. So once we had the alpha or the beta written down, then we rewrote it. So this is saying the tangent of alpha is equal to v over 3. And then I made a triangle. I said, okay, here's alpha. Tangent is opposite v over adjacent 3. And now I'm going to use the Pythagorean Theorem. So a squared plus b squared equals c squared. So 3 squared plus v squared equals c squared. So 9 plus v squared equals c squared. So c is going to be plus or minus the square root of 9 plus v squared. And again, in these problems, we're just dealing with the positive part. And also it's a hypotenuse, so it would definitely be the positive. Yeah, so we're not going to include the 2. So we're going to take care of the 2, but we're going to let the 2 be taken care of by the identity. So we're only going to take the inverse trig part and set that equal to some angle. Does that make sense? And I'm going to show you what we're going to take, how we're going to take care of the 2 part here in a second. But any questions on what I did so far? Okay, so right now my problem, right, I started with the sine of 2 tangent inverse v over 3, and now I've reduced it to being the sine of 2 alpha. So if I go to my identity sheet, there's not a sine of 2 alpha, but there is one that is the sine of 2 theta. And the sine of 2 theta is 2 sine theta cosine theta. So what that means is basically instead of thetas, I have alphas. So our problem is going to turn into 2 sine alpha cosine alpha. And now off of my triangle, I can read the sine of alpha and the cosine of alpha. So I have 2. The sine of alpha is v over the square root of 9 plus v squared. And the cosine is 3 over the square root of 9 plus v squared. So before I multiply that out, questions? No. Okay, so then if I go to multiply, you can think of the 2 as really being 2 over 1. So the 2 is in the top. So in the top, I have 2 times v times 3. So that's going to give me 6v. And on the bottom, oh, sure. Yeah, let me know when you're ready for me to go on. Not a problem. Sorry about that. Okay, no problem. So on the top, I have 2 times v times 3, so that gives me 6v. And then on the bottom, I have 1, but I don't really need to multiply the 1 times anything, right? Because nothing's going to change. And then I have the square root of 9 plus v times the square root of 9 plus v. So anytime, and this is kind of just in general a little side note, right? Anytime you have the square root of a bunch of stuff times the square root of the same stuff, the square roots basically can't go away, and this just leaves you with the stuff, right? So square root of 9 plus v times the square root of 9 plus v is just going to be 9 plus v squared. Whoops. Square root of 9 plus v squared times the square root of 9 plus v squared is just going to be 9 plus v squared. So that's your final answer. So that's what they mean by an expression in v, right? So my final answer has v's in it, and that's okay. Questions? So, that is the end of kind of like just applying the identities, all of that stuff from section 5.2 to 5.4. So the identities aren't going away. We're still going to use them. Okay, if you made, the problem is if you made alpha equal to the whole entire thing, right? So like if you said let alpha be equal to 2 tangent inverse of v over 3, the problem here is before you could rewrite it, you would have to solve for the inverse tangent. So if I divided both sides by 2, I'm going to have alpha over 2 is equal to the tangent inverse of v over 3, or that the tangent of alpha over 2 is equal to v over 3. And so the problem is you would get the same triangle, except that the angle inside the triangle now is going to be alpha over 2. And so now you're just left with, when you like plug back into your original problem, now you're just left with the sine of alpha, and there's nothing for you to do with that. But your triangle is only alpha over 2. So you run into a problem. So you can still do it, but it's going to take a lot more work, and it's going to make you're going to have to get creative with how you use the identities. So like you could do it because you could say, okay, well, sine of alpha over 2, the sine of alpha over 2 is the sine of 2 times alpha over 2. And so I know the stuff about alpha over 2 off the triangle. And now I'll apply the identity. So now it would become the sine of, or 2 sine of alpha over 2 cosine of alpha over 2. So you can get there, but it's not straightforward anymore. So my recommendation would be, don't make alpha equal to the whole entire inside. Just make your alpha and your beta and those things equal to just the inverse trig part. So it's not that you can't do it. You can, but it's not going to be as straightforward if you do it that way. Does that answer your question? No problem. Other questions? No? Okay. So then that was the end of applying the identities, just kind of straight up applying them. So now what we're going to do is we're actually going to turn to kind of like the biggest thing that's left for us to do in trigonometry. And so the biggest thing that's left for us to do in trigonometry is being able to solve trigonometric equations. So if you have to go on to calc, into the calculus sequence, right, we end up solving trigonometric equations kind of a bunch of times. So kind of interestingly, right, so there's still, right now we're in week 8 of the semester, so we're only halfway through the semester, but after we're done with section 5.5, so there's still a bunch of stuff we're going to learn for the rest of the semester. There's still, obviously, 2 more tests and then the final exam. However, all of the stuff the majority of the stuff that's on the final exam, we will have learned after we've done section 5.5. Not everything, but most of the stuff that I put on my final exam actually comes, is prior stuff up to and including the solving trigonometric equations. And so solving trigonometric equations is one of the most important topics that we're going to kind of cover. So this is section 5.5. So trigonometric equations. Will the stuff we did on test 1 also be on test 2? Okay, so there's not like repeat problems, say, from test 1 to test 2. However, we have, if you remember, so the big thing about test 1 was knowing the unit circle and being able to use the unit circle. So for test 2, you still have to know the unit circle, because we use the unit circle in section 4.7, and we're actually going to use the unit circle again today a lot. So that's kind of like the important part from before. So there's not going to be problems where I ask you what's the cosine of this or what's the tangent of this, but it's kind of like trig kind of builds on itself, so you can't forget that stuff, because it is being used like in the background. Does that make sense? No problem. Other questions? Okay, so we're going to look at things today that kind of look like this. Say, I want to know, when is the sine of theta equal to 1/2? So if we think about what the graph of the sine of theta looks like, right? So remember, the sine of theta, one period looked like this, but remember it keeps going forever and ever. And remember, this here was 2 pi. This was pi, right? Pi over 2, 3 pi over 2. It was 1 tall and 1 low, right? So that was the basic graph of the sine function. So we're interested in when is the sine function equal to 1/2. So if you think about it, 1/2 is here, and I could think about drawing the line y equals 1/2, right? So we're looking for all of these places where this pink line intersects the sine graph. And remember, the sine graph goes forever and ever. So there are an infinite number of solutions to the sine of theta being equal to 1/2, right? So when we're solving trig equations, what's going to end up happening is they're kind of going to be presented in two different ways. So one of the ways they could be presented, so two, we'll call it presentations for solving trig equations. And so we'll kind of put a line here down the middle. One is you can see things like solve the sine of theta equals 1/2 on the interval from 0 to 2 pi. Right? So remember, 0 to 2 pi is once around the unit circle. So we're talking about what are all the values once around the unit circle. So the unit circle is going up here to 2 pi. So if we're talking about solving just on the unit circle, just on the interval from 0 to 2 pi, we're talking about this answer and this answer here. And you can either, so if you remember your unit circle, then anybody remember when is the sine equal to 1/2? Yep, so at pi over 6 and at 5 pi over 6. So this first place here, this is pi over 6, and this second place here is 5 pi over 6. So theta could be pi over 6, or theta could be 5 pi over 6. Right. So one type of the problems usually say, hey, solve these problems basically between 0 and 2 pi. So they're talking about solve it on the unit circle. The other problem says find all solutions, and it doesn't give an interval. Sometimes it might say, rather than find all solutions, it might say solve over all real numbers. So here they're not giving you an interval to break it down. So the thing is I want every single possible place that the sine value is equal to 1/2. And so you might go, okay, well, I could start writing them down. They would be pi over 6, 5 pi over 6, right? Oops, pointing at the wrong place. 5 pi over 6. The next place is going to be here, right? So I can figure out what that is and then what this is. And then I could keep going. Now, obviously, right, there's going to be more places out this way. There's these 2 points. I can go out to the left. Obviously, I'm not going to sit down and write out individually all of the answers, okay? One of the reasons why is because you would never finish the problem, right? There's an infinite number of places this happens, so I can't actually write out every single answer because it happens an infinite number of times. And so, you know, I don't think you want to spend the rest of your life solving this one trig problem, right? I think probably for a lot of you guys, you might be like, wow, that is a terrible idea, right? That sounds like the worst idea ever. You know, the worst thing ever, and we're living in a pandemic, right? So it'd be pretty bad to be like, the worst thing ever would be solving a trig equation for the rest of my life. So we want a better way to do that. We want to know what every single solution is, but we kind of need to figure out a way to write them. So the way to write them is, what we do is we generally start with the solutions that are on the unit circle. So we say, okay, well, theta is, we're starting off with, it could be pi over 6, or theta could be 5 pi over 6, right? Those were the two solutions we got off the unit circle. And then the thing is that the distance between this first solution and this second solution is 2 pi. It's basically, I go around the unit circle once and then I go a little more, right? If I were to go from this one to the next solution out here, it would be another 2 pi. So I would keep going a 2 pi amount. If I went from this first solution out here to this one it mirrors over here, I went backwards 2 pi. So I'm going minus 2 pi. So to hop from solution to solution, I'm either going forward some number of 2 pi or I'm going backwards some number of 2 pi. And the way that we mathematically write that is, you'll see it written as plus 2k pi, where k, and we do this funky math thing, so it has k, it looks like a little e that's written kind of weird, and then this fancy z. And so what this part is saying, this part here is saying k is in the integers. So the little e part is saying this is a member of. So it's mathematically how we say is a member of, or it's in. And then this z with like this kind of extra bar here. On Alex or in a textbook, it might be a bold, right? But it's hard for me to write the bold. So it would be saying k is an element of the integer. So what it's saying is, start at pi over 6 and then jump some number of 2 pi's, right? So maybe I go 3 2 pi's, right? So I would go out 1, 2, 3 more someplace out here to get that next answer. Or maybe I go backwards 1 2 pi. So start here and go backwards a 2 pi. So the plus 2k pi is basically moving you. It's saying go around the unit circle some number of times and then go to pi over 6. And so that would be the same thing here. 5 pi over 6 plus 2k pi, again, where k is in z. Brendan, I saw you put what the question. Can I help clear something up? Yeah, it's super weird looking, and it's so this is a very common thing in math. If you have functions that cycle, so the sine function and the cosine function cycle, and so the way to write an infinite number of solutions is this: pick the first point on the cycle, the first time you see it on the cycle, and then keep adding however many cycles you need to get around. So it is a very odd thing the first time you encounter it. Questions? Okay. So the K and Z is basically just saying, so let me actually add in here a unit circle so that I can actually put it in here small enough. Okay. So let's take this value here at pi over 6. That's the first time that I like find some place where the sine value is equal to 1/2, right? So that's where I get this first answer, the pi over 6. That's what I did on this side, right? I just got pi over 6. I can, if you think about it, so every time an angle, right, we talked about how coterminal angles have the same sine and cosine value. So I could get to the answer just by rotating and stopping at pi over 6, or I could rotate all the way around and stop a second time at pi over 6. Or I could rotate around 1 time, 2 times, 3 times, 4 times, and stop at pi over 6. And that would still give me an answer of 1/2, right? So I could go around the circle as many times as I want and stop at the pi over 6, and I'm still going to have the answer, the sine value, be 1/2. Does that statement make sense? The idea that I can rotate around the unit circle as many times as I want and stop there. Okay, so remember, if I rotate around the unit circle once, I've gone an additional 2 pi. If I go around the unit circle twice, I've gone 4 pi. If I go around 3 times, right, I've gone 6 pi. I could also go negatively, right? So I could go around the unit circle in the opposite direction once. That would be minus 2 pi. Or twice, that would be minus 4 pi. Or 3 times, that would be minus 6 pi. And I could continue this, right? So I keep getting all of these basically even integers times pi. Does that statement make sense? Okay. All this part here is saying it's saying that. So if you think about it, if k was 1, then I have 2 pi. If k is 2, then I have 4 pi. If k is 3, I have 6 pi. If k is 4, I have 8 pi. If k is 5, I have 10 pi. If k is 6, I have 12 pi, right? Or if k is negative 1, I have minus 2 pi. If k is negative 2, I have minus 4 pi. If k is negative 3, I have minus 6 pi. So all this is doing is saying go around the unit circle some number of times. That number of times is k. So either go once around the unit circle, or twice, or 3 times, or 4 times, or 5 times, or 6 times, or 100 times if you wanted, or go in the opposite direction, so go minus 1 times, or minus 2 times, or minus 3 times, or minus 4 times, or minus 100 times. So this is just the mathematical way of writing all of these possible values out, right? Without having to write them all out, because it's an infinite number of things. I can't write them all out. Does that help clear up what the k and z is? So z stands for the integers, and so the integers, right? So z is standing for the integers, and so if you think about the integers, they're all the whole numbers, all the positive and negative whole numbers. So like 0, 1, 2, 3, 4, ... and minus 1, minus 2, ... going down that way. So z is the mathematical way of writing every single positive and negative whole number without actually having to write them. Does that help? No problem. Other questions? It's a weird notation the first time you see it. Okay, so then let's try. So the first ones we're going to do are find all solutions of the equations in the interval 0 to 2 pi. So all the problems we're going to do right now are we're just going to look once on the unit circle. We'll come back and do more of those ones with the plus 2k pi part. So let me add in here my unit circle. That way we just kind of have it sitting here to help us out. Okay, so my first big one is going to be the cosine of theta equal to 1. So where on the unit circle, right? So we're solving in the important thing here is solving in the interval 0 to 2 pi. That's telling me I just have to look on the unit circle. So where on the unit circle is the cosine of theta equal to 1? Okay, so it's equal to 1 correct, it's equal to 1 at 0. It's equal to 1 at 2 pi. The thing you want to be careful of is 2 pi here has a parenthesis, which means we can't give 2 pi as an answer. We're going all the values up to 2 pi, but we're not actually giving 2 pi itself as an answer. So the answer here would be 0. Theta would be 0. Try another one here. What about the sine of theta being equal to, we'll say, 0? So where are all the places that the sine of theta is equal to 0? Yeah, 0 and pi. So remember, the sine is the y value. So the y value is 0 at 0. So theta could be 0. Or also at pi. Theta could be pi. C, the tangent of theta, not equals to, plus 1 equals 0. Okay, so we're stepping it up a little bit here, right? A, because it's a tangent problem. But B, as opposed to my first two problems here, where I had the trig function isolated all by itself, in this third function, I do not have the trig function all by itself. So the very first thing we're going to do if we're solving a trig equation and the trig function is not all by itself, we're going to isolate the trig function. We're going to work to get the trig function all by itself. Kind of just like when we're solving an equation and it has x's in it, we try to get the x all by itself. Same deal here. So the first thing I'm going to do is I'm going to subtract 1 from both sides. So we're really trying to solve the tangent of theta being equal to -1. And so when is the tangent of theta equal to -1? Yep, so 7 pi over 4 and 3 pi over 4. So theta is going to be 3 pi over 4, 7 pi over 4. Questions? Okay, do one more here. What about 2 sine theta plus square root of 3 equals 0? So again, I have to isolate the trig function. So the first thing I'm going to do is I'm going to take that root 3 and move it to the other side. So we have 2 sine theta equals minus root 3. Divide both sides by 2. So we're looking for when is the sine of theta equal to minus root 3 over 2? So what do we think? 5 pi over 3, yep. It's definitely one of the places. And where else? Yeah, 4 pi over 3. So theta is going to be 4 pi over 3 and 5 pi over 3. All right, so I'm looking for the places on the unit circle where the y value is minus root 3 over 2. So this is kind of similar to what we were doing when we were doing the inverse trig functions, right? And people often get confused. Wait a minute, when am I supposed to do what? The inverse trig functions, we had those restrictions and those quadrants we had to like look for, and then we had to rewrite stuff as negative if it was in the fourth quadrant as a negative angle. Here, solving trig equations is easier. It's just looking at the unit circle as it is and pulling off all the possible values that it holds true for. All right, so let's try another one here. So sine of theta times 2 cosine theta minus, root 3 equals 0. Okay, so I've got two different pieces here being multiplied together, right? I have the sine theta part, and then I have the 2 cosine theta minus root 3 part, right? So if you think back to algebra, like what do we do, like when we were doing stuff in math 126, what did you do if you had x minus 2 times x plus 1 equals 0? How did you solve that? Okay, so it would be x equals 2 and x equals minus 1. And right, so the reason how we solve it is we take each piece and we set it equal to 0, right? So we took the x minus 2, set it equal to 0, that gives us the 2. And the x plus 1, set it equal to 0, that gives us the minus 1. We're going to do the same thing with our trig functions here. So I have two different pieces, and multiplied together, they're equal to 0. So we're going to set the first piece equal to 0. So the sine of theta could be equal to 0. Or the second piece, 2 cosine theta minus root 3, that's equal to 0. Right? So I've got the two different pieces. I'm taking each piece and setting each piece equal to 0. And then we'll work with each piece. So the first piece, we're looking for where the sine of theta equals 0. So we've already even solved that today, right? Where is the sine of theta equal to 0 when theta is equal to what? Yeah, 0 or pi. And then the second piece, we have to first solve for the cosine of theta. So 2 cosine theta is going to be equal to root 3. Divide both sides by 2. So the cosine of theta is going to be root 3 over 2. So when is the cosine of theta equal to root 3 over 2? Yep, pi over 6. And so not 5 pi over 6, but 11 pi over 6, right? So theta is going to be pi over 6 and 11 pi over 6. So this problem here has 4 answers, right? Theta could be 0, it could be pi, it could be pi over 6, or it could be 11 pi over 6. Excuse me. Questions? Pi over 6 and 11 pi over 6. I can move that up. Does that help? Can you? No problem. Other questions? Okay, so let's try some more. I'm going to go to another page. All right, oops, I don't remember what, no, okay, we did E. So F. Oops. Help if I drew. Okay. 3 tangent squared x minus 1 equals 0. So again, I want to try to solve for the trig function first. So there is only one instance of the trig function. So I can at least get the part with the trig function by itself. So the first thing I'm going to do is I'm going to add 1 to both sides. So we're going to have 3 tangent squared x equals 1. And then to get the trig function by itself, I would need to divide both sides by 3. So divide by 3, divide by 3. So I have tangent squared x equals 1/3. So I'm close, right? I have the trig function by itself, but I still have a little bit of an issue going on because my trig function is squared. It's not like I'm saying the tangent of x is equal to 1/3. I'm saying the tangent squared is equal to 1/3. So any guesses what I could do to get rid of the square? Yeah, exactly. Take the square root of both sides, just like you would do if you had x squared equals 1/3. You take the square root. So same thing. So we're going to take the square root of the left side. Remember, when we do the right side, we're going to get plus or minus. So we're going to end up with the tangent of x is equal to plus or minus. And the other thing I can do is I can break up, if you have the square root of a fraction, you can make it the square root of the top number divided by the square root of the bottom number. So what we're saying is that the tangent of x is equal to plus or minus 1 over the square root of 3. So I'm looking for where the tangent of x is equal to positive 1 over the square root of 3 and where the tangent of x is equal to negative 1 over square root of 3. So again, I think I said this when we were doing the inverse trig functions, but you can go through all of these points here and do y divided by x, y divided by x, y divided by x, y divided by x, to figure out what the values of the tangent are on this whole entire unit circle, right? If I did it for the ones in the first quadrant, 1/2 divided by root 3 over 2, this would give me 1 over root 3. Root 2 over 2 divided by root 2 over 2 is going to be 1. Root 3 over 2 divided by 1/2 is going to be root 3. And 0 divided by 1 is 0. 1 divided by 0 is undefined, right? So those are the values of the tangent. And then those values will repeat on the other pieces, but they'll be different, like positive or negative, right? So here in the second quadrant, this is going to be minus root 3 for the tangent, minus 1 for the tangent, minus 1 over root 3. This is still just going to be 0, right? In the bottom, again, now it's going to go back to positive root 3, positive 1, positive 1 over root 3. And then this again would be undefined. And then finally, again, minus 1 over root 3, minus 1. Oops, I did that. What did I do wrong there? Oh, I did this would be 1 over root 3. I'm like, this is wrong. This one's wrong. This would be positive root 3. It would help if I could reflect correctly, right? And then this would be positive root 3 minus 1, or minus root 3 minus 1 minus 1 over root 3. So anyway, sometimes it's helpful to do all that, right? So you can see the values of the tangent. Okay, so now that I did all that for us, where is the tangent equal to positive 1 over root 3 or negative 1 over root 3? So Liana said pi over 6. So yep, that's definitely one of them. Where else? Okay, 11 pi over 6, yep. So that's where it's equal, so 7 pi over 6, yep. and 5 pi over 6. Yep. So those places. Questions? No. And I'm going to cheat a little bit since, oops, I want to, I'm just going to make that a little bit smaller so I have a little more room to do my next problem. So G is going to be 4 sine squared x cotangent x minus 3 cotangent x equals 0. Okay, so this one looks a little uglier, right? So again, just like if you had just x values, sometimes you have to factor first when you're going to solve an equation equal to 0. Same thing here. It's just that we're factoring out trig functions. So if I look at my two pieces, my first piece is this 4 sine squared x cotangent x, and my second piece is this 3 cotangent x. Is there anything similar? Is there anything the same between those two pieces? A common factor that I could pull out? Yeah, the cotangent. So if I factored out the cotangent, I'd have cotangent x times 4 sine squared x minus 3 equals 0. And then we did a problem already where we had one trig function times another trig function. So we're going to set each of these pieces to 0. So the cotangent of x is going to be equal to 0. Or 4 sine squared x minus 3 is going to be equal to 0. So cotangent of x equal to 0. So remember, cotangent is x over y. And you essentially could flip all of the tangents. The thing is when you flip something that's undefined in terms of the tangent is undefined, the cotangent would turn out to be defined. So the cotangent is actually going to be 0 at these two places where the tangent is undefined. Because the cotangent is x divided by y. So 0 divided by 1 is 0. 0 divided by negative 1 is 0. So the places the cotangent is 0 is when x is equal to pi over 2 or x is equal to 3 pi over 2. And then solving 4 sine squared x minus 3 equals 0. That's very similar to what we just did in part F. So I'm going to move the 3 over. So sine squared x, 4 sine squared x is going to be equal to 3. I'm going to divide both sides by 4. And I'm going to rewrite it up here just so I don't get too low for people. So this is going to be sine squared x equals 3 over 4. And then just like before, I'm going to take the square root of each side. Remember, I take the square root, I'm going to get plus or minus. So sine x is going to be plus or minus root 3 divided by root 4. But remember, root 3 divided by root 4 is 2. So we're looking for when is the sine of x equal to plus or minus root 3 over 2. So that's going to happen when x is what? Pi over 3, yep. Anyplace else? 2 pi over 3, yep. Anyplace else? 4 pi over 3, yep. And 5 pi over 3. Yep. So basically all the pi over 3s, right, are all the places where it's plus or minus. So in this problem, you have 6 answers, right? I have pi over 2, 3 pi over 2, then pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Questions? Does anybody need me to wait before I go to the next page? No. Okay. Record. Okay, so now we're going to go back to those, plus 2 k pi, k is in z problems. So we're going to find all solutions to the equations. Right, so notice the important thing to notice here is they didn't give me that interval from 0 to 2 pi. I'm still going to add my unit circle in here for us to kind of have, right, as a reference, because we're still going to need to find the values on the unit circle, and then we're just going to add that plus 2k pi to our answers. So, 3 square root of 2 plus 6 cosine x equals 0. So the first steps, the only thing that's different is at the very end of the problems. The first steps are still the same as the first steps we were just doing. So I still want to isolate the trig function. So I'm going to subtract that 3 root 2 to the other side. So we're going to have 6 cosine x equals minus 3 root 2. Divide both sides by 6. So the cosine of x is equal to, so if I divide by 6, I end up with minus root 2 over 2. All right, so the first step is to figure out where is the, when is the cosine equal to minus root 2 over 2? So, okay, 3 pi over 4, yep. So one of the answers is going to be, so 3 pi over 4, and where else? 5 pi over 4. Okay, so those are the two off the unit circle. If the problem had said solve this between 0 and 2 pi, I'd be done. But it didn't say solve it between 0 and 2 pi. It said find all the solutions. So if it says find all the solutions and it doesn't give you 0 to 2 pi, that's the thing you're looking for. 0 to 2 pi in the problem stated, you just have to pick the stuff off the unit circle. If it doesn't give the 0 to 2 pi, what you have to do is you have to add plus 2k pi plus 2k pi, where k is an integer. Okay, so you're always adding the exact same thing. Alex will have a way to pick this, right? It'll have a plus, sometimes it'll have plus 2k pi, k is in z already there, and you just have to click a button and it'll just pop that part in for you. So Alex will allow you to put that in, so just to be aware of that. So that's all there is to the problem. So it's just this minor tweak at the very end of the problem. Questions? Yeah. All right, we'll do one more. I think I have time for it. So 3 tangent x plus 1 equals minus 2 times 2 plus tangent x. So the first thing I need to do in this problem is remember I'm trying to isolate the tangents, but I have tangents on both sides of the equation. So I'm going to want to get them together. But before I can do that, I need to distribute that negative 2. So we're going to have 3 tangent x plus 1 equals minus 4 minus 2 tangent x. So if I add 2 tangent x to both sides, I would end up with 5 tangent x plus 1 equals -4. If I subtract 1 from both sides, I have 5 tangent x equals -5. And now I'll divide both sides by 5. So I have the tangent of x equals -1. And so when is the tangent of x equal to -1? When x is equal to what? Okay, 3 pi over 4 and 7 pi over 4. And then all I have to do is add that plus 2k pi, where k is in z. And so Alex will take this answer. You just have to put both of them in. Alex might, on a tangent problem, say, hey, did you know you could be clever and write it as one thing? And you can only do this for the tangent. If you think about the tangent, I have pi over 4 here, and I have 5, oops, wrong one. I have 3 pi over 4 here, and 7 pi over 4 here. So you could have written it as plus k pi and just kept bouncing back and forth along this line. So Alex might try to tell you that, but it's going to take this as your answer. And so generally students just prefer the one method all the time. And so that one method all the time is just always put plus 2k pi. And we're going to do more problems next class. So it is 3:20, so we'll stop now. But that gives you a good idea of kind of what we're beginning to do. And then next class, we're going to look at some special cases of some special techniques to solve these things. So to solve ones that are a little more complicated. We kind of got the basics down for right now. So have a good weekend. If anyone has any questions and wants to stick around, more than happy to answer them. Otherwise, I will see you guys all on Monday.